This is the screencast for section 8.3, example 2. So we're going to compare natural log of x with x and x squared as x approaches infinity. So we're going to show in example 2 that the natural log of x, one of those basic comparisons that we showed in previous example 1, grows slower as x approaches infinity than ax and then bx squared. So we're going to show that it grows slower, which I think then I'm going to look for natural log of x in the numerator and then x in the denominator, and I'm looking for a limit as x approaches infinity of 0. Well, right now, if I plug in infinity, or just think about what happens as x approaches infinity, I get infinity over infinity. So I need to use L'Hopital's. So the derivative of the numerator is 1 over x, and that's over 1. So now 1 over infinity is 0 over 1, so I do get a limit of 0. Now I can make that conclusion that the natural log of x grows slower than y equals x as x approaches infinity. Now how about x squared? Again, if I'm going to show that the natural log of x grows slower, I'm going to try putting the natural log of x in the numerator and x squared in the denominator as x approaches infinity, taking that limit, and hopefully I get a limit of 0. I could put x squared in the numerator and natural log of x in the denominator, hope to get a limit of infinity, which would still show that x squared grows faster than natural log of x, and therefore natural log of x grows slower, but I think this is a more efficient way to go, let's say. Now, as x approaches infinity here, I'm going to get infinity over infinity. So I'm going to use L'Hopital's. Derivative of natural log of x is 1 over x. Derivative of x squared is 2x. I'm going to simplify a little bit by multiplying both the numerator and denominator by x. Now, the limit as x approaches infinity of 1 over 2x squared, 1 divided by a really, really large number, is going to be 0. So I can make my statement then that y equals natural log of x does in fact grow slower than y equals x squared as x approaches infinity. Now try problem number 5. It says, show that the natural log of x grows slower than the given function. Well, again, if I'm looking for growing slower, I'm looking for a limit of 0. That's more efficient. So I'm going to put the slower one on top, so that would be natural log of x, and then x minus natural log of x in the denominator. Well, as x approaches infinity right now, I get infinity over infinity. Then I'm going to use L'Hopital's, so 1 over x over 1 minus 1 over x, which is messy. So I'm going to multiply both the numerator and denominator by x. Simplify, that's a little less messy. 1 over infinity then is going to be 0. So the limit as x approaches infinity of the natural log of x over x minus the natural log of x is in fact 0 by L'Hopital's. So I can make the conclusion that y equals natural log of x grows slower than y equals x minus the natural log of x as x approaches infinity. In other words, the denominator is going to get larger a lot faster than the numerator is because the denominator is growing faster, the numerator is growing slower.